Okay, so today we're going to talk about 7.3 hypothesis testing for the mean. And here we're still looking at the same process we've been doing. The only main difference is now instead of small samples, I'm going to cross that out. And we're going to actually say this is when sigma, or a population standard deviation, is unknown. Okay, so when sigma is unknown. So in section 7.2, you learned how to perform a hypothesis test for a population mean when the population standard deviation is known. In many real-life situations, the population standard deviation is not known when either the population has a normal distribution or the sample size is at least 30. You can still test the population mean mu. To do so, you can use the t-distribution with n-1 degrees of freedom. So the first thing we're going to talk about is how we find the critical values in a t-distribution. And the main thing that we need to remember is the first thing is we need to always know or to specify the level of significance. And remember, this is always given to you in the problem. Sorry, my pen stopped working there for a second. And that's going to be alpha. Okay, the second thing is we're going to identify the degrees of freedom. So we're bringing back that idea of the degrees of freedom, which remember is going to be abbreviated DF. And we find that by doing n-1. And then we're going to, there we go. Okay, so then we're going to find the critical value. From table 5. Okay, so we have 3 conditions. So the first one is if it's left-tailed. Then we're going to look at our one-tailed row. With the degrees of freedom. And the key thing here is you're going to have a negative critical value. And here, instead of z sub 0, we're going to use t sub 0 for the critical value. Okay, our second condition is if we're right-tailed. Then again, we're going to look at our one-tailed row with the given degrees of freedom. And we're going to have a positive critical value, t sub 0. And our third type we can see is two-tailed. And this is when we're going to look at the two-tailed row. With whatever degrees of freedom we find. And here we're going to have a plus or minus critical value, t sub 0. Okay, so remember, the left-tailed, right-tailed, and two-tailed are always going to come from our alternative hypothesis. Or H sub A. Okay. All right, so if we want to find these, so find the critical value t sub 0 for a left-tailed test with alpha equaling 0.01 and n equaling 14. So from n equaling 14, we know our degrees of freedom equals 13. And since it's left-tailed, that means it's going to be one-tailed. So our critical value, since it's on the left, is going to be negative. Okay, and I'm going to jump screens real quick, and I'm going to look at that table 5. All right, so we know, let me get the highlighter. Okay, So we said it was left-tailed, so we're looking at one-tailed for 0.01. And our degrees of freedom, we said it was 13. Okay, so where those match up, so our critical value is going to be negative 2.65. Okay, so if we look at the next one, find the critical value for a right-tailed test with alpha equaling 0.05 and n equaling 9. Our degrees of freedom equals 8. So again, I'm going to jump over. So now we're looking at when our degrees of freedom is 8 and alpha is 0.05. So we're one-tailed and 8, so that makes our critical value is 1.860. And it's going to be positive because it's right-tailed. Oops. Okay. And then lastly, we're looking at a two-tailed test with alpha equaling 0.01. And since n equals 16, our degrees of freedom is going to equal 15. Okay, so last time I'm going to jump over once more. Oops. Erase what we had here. Alright, so two-tailed means we're looking at this next row. So two-tailed for 0.01. So we're looking at this far right column. And our degrees of freedom was 15. So if we line those up, that means that our critical value is 2.947. Okay, and then remember, since it's two-tailed, our critical value is going to be plus or minus. So we have plus or minus 2.947. Okay, so for the most part, that's the same process as what we did with 7.2, except for when we looked at table 5, we looked at the infinity row. Okay, all right. Okay, so if we want to test for a mean mu when n is less than 30 and sigma is unknown, and this n is less than 30 isn't necessarily going to always be true. Okay, we will look at an example when n is greater than 30. Okay, so this is called the t-test. For mean mu is a statistical test for a population mean. The t-test can be used when the population is normal or nearly normal, sigma is unknown, and n is less than 30. The test statistic is x bar, and the standardized test statistic is t. So our new formula, t equals x bar minus mu over s divided by the square root of n. Okay, so that's very similar to the formula we used in 7.2, except for we're going to use everything from the sample rather than the population. So our guidelines, or our steps for hypothesis testing, are going to be very similar to what we saw in 7.2. So first thing we want to do is we want to verify that sigma is unknown. The sample is random. And either the population is normally distributed, or n is greater than or equal to 30. Okay. Step 2, we're going to state the claim. The null hypothesis, and the alternative hypothesis. And those are going to all be the same process as what we did last section. Then we're going to specify alpha. Then we're going to identify the degrees of freedom from n minus 1. Then we'll use table 5 to find the critical value or values. And remember, that's going to be t sub 0 here. And from that, we're then going to find the rejection region. We're going to find and sketch the rejection region. Okay, step 7, we're going to calculate the standardized test statistic. And remember, that's our formula: t equals x bar minus mu over s divided by the square root of n. And once we know that test statistic, we can determine if it falls in the rejection region or not, which is going to allow us to make a decision. Okay, and remember, our two decisions are either to reject the null hypothesis or fail to reject. And then lastly, we're going to interpret the decision in context with the claim. Okay, so the same steps for the most part that we did in 7.2 with rejection regions. The only thing that's really different, which adds that additional step, is identifying the degrees of freedom. And then here we're going to always use table 5. Okay, if for some reason when the degrees of freedom, you need, well, that, I'm not sure what happened. There we go. Okay, so when the degrees of freedom, okay, I'm having issues here. We're just going to do it this way. There we go. When the degrees of freedom you need is not in the table, use the closest degrees of freedom in the table that is less than the value you need. For instance, for degrees of freedom 57, use 50 degrees of freedom. Okay, you shouldn't run into that issue, but just in case, I wanted you to remember that. All right, so I'm not sure why this ended up on 2 pages, but we're going to do our best. So, a used car dealer says that the mean price of a 2-year-old sedan in good conditions is at least $20,500. You suspect this claim is incorrect and find that a random sample of 14 similar vehicles has a mean price of $19,850 and a standard deviation of $1,084. Is there enough evidence to reject the dealer's claim at alpha equals 0.05? Assume the population is normally distributed. All right. So first thing we want to do is we want to state our null and our alternative hypothesis and determine which is our claim. So from the first sentence, we know that the claim is at least 20,500. So at least would be greater than or equal to. So that would be the null. Because remember, the null hypothesis always has equality in it. the 20,500, which means our alternative hypothesis is going to be less than 20,500. And then our null is our claim. Okay, so now I'm going to go through and I'm going to state everything we know. So we know that the sample size is 14, which means our degrees of freedom is 13. We also know that the sample mean or sample mean price was 19,850. And the sample standard deviation was 1,084. And lastly, we know alpha equals 0.05. Okay. We know since it's less than that this is going to be left-tailed. So I'm going to go ahead and sketch our graph. Show that it's going to be left-tailed. And then we want to find our critical value. So using table 5, degrees of freedom 13, and we're one-tailed at 0.05 level of significance. That tells us that our critical value, and I found this early, I'm not going to make you jump back and forth again, is going to be negative 1.771. Okay. So now we want to find our standardized test statistic. So t equals x bar minus mu over s divided by the square root of n. So if we plug everything in, we have 19,850 minus 20,500 divided by 1,084 over the square root of 14. And if you plug that in your calculator, and I rounded to 2 decimal places, make sure when you're doing your homework and your quiz you check to see if it wants it to 2 or 3. So we get negative 2.24. So if we look at where that falls in, my goodness gracious. There we go. Sorry about that. Okay, so if we look and see where that falls in our graph, negative 2.24 would fall to the left of our critical value, which means our decision is going to be to reject the null hypothesis. And our interpretation, so at, let's see here, 5% level of significance, there is enough evidence so our claim was in our null, so that means there's enough evidence to reject the claim. That the mean price is at least $20,500. Okay. All right. Now looking at this last one. An industrial company claims that the mean pH level of the water in a nearby river is 6.8. So right there, that tells us that our claim is 6.8. And since is would be equals, that's going to be our null. So that means our alternative hypothesis is that mu does not equal 6.8. And since it's not equal, we already know it's going to be two-tailed. So if you want, you can go ahead and sketch your graph. And we're going to have two critical values, one negative, and 1 positive. Okay, so now looking at the rest of the question, you randomly select 39 water samples, so n equals 39, and measure the pH of each. The sample mean and standard deviation are 6.7 and 0.35 respectively. Is there enough evidence to reject the company's claim at alpha equals 0.05? Okay, so since n equals 39, that means our degrees of freedom equals 38. And you can find that value in your table 5. Okay. So if you look at table 5 and you looked at row 2-tailed, degrees of freedom 38 at alpha is 0.05, you will find that your critical values are 2.024 plus or minus. Okay. Now we want to find our test statistic. So T equals x bar minus mu over S divided by the square root of n. So we have 6.7 minus 6.8 over 0.35 divided by the square root of 39. And if you calculate that, you get approximately negative 1.78. Okay, so looking at our rejection region in our graph, that t value would fall in between. And since it's in between, that means our decision is going to be to fail to reject. Okay, so at 5% level of significance, there is not enough evidence to reject the claim that the mean pH level of the water equals 6.8. Okay, so again, it's the same process as 7.2 with rejection regions. In 7.2, we also looked at using p-values for t-test. For this, you have to use a graphing calculator, so we are only going to look at rejection regions. You do not have to worry about using the p-values. Okay. If you have questions, make sure you're emailing me. Come see me during an office hour if you need any help. Your required work for this week is the 7.3 homework. If there's an optional 7.3 quiz, if you choose to take it, make sure you turn in the scratch paper for that though.